there, it's Ian Shapiro, and I'm going to talk a little about how to understand heat pumps through the lens of temperature. Temperature is really helpful for understanding how they work, and then how they work inefficiently and how they work efficiently and more efficiently, all through the lens of just of temperature. Bear with me. So if we look at the temperatures of a heat pump, we might think about the indoor air that we want to heat in winter being at 70 degrees Fahrenheit. And outdoors it's going to be cold, so let's just assume it's going to be 30 degrees Fahrenheit for this example. Well, how does a heat pump get heat out of this cold outdoor air? And the answer is it gets it by putting refrigerant in the outdoor heat exchanger that is colder than the outside air. And as a first example, you might consider that refrigerant being 30 degrees colder than the outside air. So the refrigerant in the outside unit is at 0 degrees. And that exchanges heat. It extracts heat from the outside air, and that heat heats that refrigerant. And in fact, it evaporates that refrigerant. And the compressor then compresses that low temperature, that low pressure refrigerant up to a high pressure and a high temperature. And that might well be 30 degrees hotter than the indoor air. And that is how the indoor heat exchanger heats the indoor air. And what's happening between 0 and 100 degrees, that's refrigerant and refrigerant, is that the compressor is compressing it from a low temperature at 0 degrees up to a high temperature at 100. And this is how a heat pump is working, and it's a great way to think about how a heat pump works, is with the indoor temperature, the temperature where the heat pump is getting the heat from, and we call that the source. This is called the source. It's getting heat from the source, it puts it into refrigerant, it pumps the refrigerant up to a high temperature, and as a first pass at those temperatures, just add 30 degrees to the temperature of the air or the water, whatever you're trying to heat, add 30 to that, just as a first estimate. And for the refrigerant, subtract 30 from the air or the groundwater, whatever it is that is your source, just subtract 30 from it. And this will be the basis for our discussions of heat pumps and temperature. And a key thing to know is that the power used by the compressor, the electricity, increases for the increase in refrigerant temperature. In this case, it's increasing it by 100 degrees, and that has a relationship to the pressure that the compressor is adding to that refrigerant. Its power depends on this temperature change from refrigerant to refrigerant. Hold that there, and we will expand on how to use this to understand efficiency. It really helps to understand efficiency and what affects efficiency with a heat pump. Now what happens when it gets colder outside? Let's take the case where instead of 30 degrees outside, it's colder, it's 20 degrees. What's happening? What happens to the system? Okay, so we've talked about 30 degrees maybe outside air temperature, and we've talked about 70 degrees indoor air temperature. And we've said that if we just subtract 30 from the outside air temperature, that might well tell us the temperature of the refrigerant, and if we add 30 to the indoor air temperature, that might tell us the temperature of the indoor refrigerant. And we've said that the change from the outdoor refrigerant to the indoor refrigerant relates to the power required by the compressor. What happens when the outside temperature gets colder? If the outside temperature gets colder, let's say it goes down to 20 degrees Fahrenheit. It goes down because it got cold outside. Well, the refrigerant in the outside unit will get colder. And it might go down to -10 Fahrenheit. And so now we're operating at -10 Fahrenheit for the refrigerant because it's 20 degrees outside. There might be a minor change up here, but not much. And the key here is that now the compressor, which is compressing from the low temperature and pressure up to this high temperature and pressure, is going to have to work harder because it's compressing over a bigger temperature change. So what happens when the outside temperature goes down? The compressor power increases. And this means that the heat pump is working harder, the efficiency is lower, it's using more power, and it happens to be when it's colder outside, the building is also losing more heat. So the capacity required goes up, but the capacity that the heat pump provides goes down, which is why we need to speed it up with a variable speed compressor. The key thing is that when the outside temperature goes down, the temperature of the refrigerant goes down and the compressor needs to work harder and the efficiency goes down. Okay, what happens if instead of an air-to-air heat pump that's operating with 30 degrees outdoors, 70 degrees indoors, let's take a case with 30 degrees outdoors, but where we're heating hot water instead. We're trying to replace a boiler that provides 180 degree hot water. Can we do that with a heat pump? Now let's use a heat pump to heat hot water. Instead of heating air directly, we'll first heat water and then that water will heat the air. Outside, we've got our typical 30-degree winter weather. What's the refrigerant temperature outdoors? We're using our rule of thumb. We're just going to subtract 30 degrees. That's the refrigerant temperature. But now instead of 70-degree air, we're going to heat it way up. Let's say we heat it up to 180 degrees hot water. And that hot water, in turn, is going to heat 70-degree air, just like we did before. But what the heat pump is doing is it's heating hot water. So what we care about is the heat pump. And what does the heat pump need to do? If we add 30 degrees to that 180-degree hot water, and we've got 210 degrees Fahrenheit. Now the compressor is needing to compress from 0 degrees all the way up to 210 degrees Fahrenheit. And the pressure, the corresponding high pressure. For this application, this heat pump will use much more energy than if it's just pumping it up to 100 degrees as we did with an air-to-air heat pump. An air-to-water heat pump that's pumping it up to a temperature, any temperature that is higher than that 100 degrees that we needed for an air-to-air heat pump is going to take more energy. And so here, if we can, instead of 210 degrees, if instead we can use a radiant floor or a radiant panel system that is operating instead of at 180 degrees, let's say it's radiant floor operating at 90 degrees, Now what's our rule of thumb? We'll add 30 degrees to 90 and the refrigerant will be at 120 degrees. That is a much lower lift. That heat pump will use substantially less energy for the same capacity as one that's replacing a boiler. It's why a direct boiler replacement with an air-to-water heat pump is such a difficult thing to do. Besides the availability of heat pumps being small, the power requirement is much greater. All right, let's talk about a different type of heat pump, and that is a heat pump water heater, like a hybrid heat pump water heater located down in your basement. The air temperature might be 60 degrees. That is pumping heat up to hot water. It's not pumping heat to air. That hot water could be at 120 degrees, it could be warmer. And so let's take a look at those temperatures and the impact on efficiency. How about a heat pump used to heat hot water? Let's take a hybrid heat pump. It's sitting in the basement. It's an air to water heat pump. The basement air is at 60 degrees Fahrenheit. The refrigerant, we use our rule of thumb, is 30 degrees. Colder than that, it might be at 30 degrees. And we're heating hot water. Well, if that hot water is at 120 degrees, we use our rule of thumb, and the refrigerant that is heating that hot water will be 30 degrees hotter than that, and it's at 150 degrees. And this, now the compressor is compressing from 30 up to 150. That's a pretty big lift. That will have a lower efficiency than a heat pump that is heating air with 30 degrees outside temperature. We do benefit from the warm basement, relatively warm basement. That's a pretty good heat source, and we're pumping it up to 150. That's high. This is a little higher than the other one, but in the final analysis, this efficiency will be slightly lower than an air-to-air heat pump because of the high water temperature. And very significantly, if you go down to the basement and turn your water temperature up to 130 or 140, what will happen? If we operate at 140 degree hot water temperature, we use our rule of thumb, and the refrigerant temperature is way up at 170, and the compressor is working even harder. So, very important set point on a domestic hot water heater that's being used for with a heat pump. The lower the set point, the lower the power, and the higher the efficiency of the heat pump. We've heard a lot about variable speed compressors, variable speed heat pumps. What's that about, and how can we look at it through a lens of temperatures? The temperature of the source, the temperature of the refrigerant on the low side, the temperature of the air, and the temperature of the refrigerant on the high side. So let's talk about temperatures and variable speed heat pumps. With a variable speed heat pump, we're able to slow the compressor down when we don't need as much capacity. And we're able to speed it up in the middle of winter when it's very cold outside, in the middle of summer when it's very hot. So let's take our old example, 30 degrees outdoors, 70 degrees indoors. And what is a variable speed heat pump doing? Well, at 30 degrees outdoors, we might, and the manufacturer might choose to slow that compressor down, and then the temperature of the refrigerant isn't quite as cold. Instead of subtracting 30 degrees, we might only subtract 20 degrees. And instead of adding 30 degrees, we might only add 20 degrees. This is 90-degree refrigerant indoors. The compressor here is working less hard. The compressor is only compressing from 10 to 90. Remember the previous example where it compressed from 0 all the way up to 100. So the benefit of a variable speed heat pump is twofold. One is when it's very cold outside, it's able to speed up because we need that capacity. And the other is when it's not cold outside, it's able to slow down, and that slowing down reduces this temperature difference. We don't need as much temperature difference because it's warmer outside. And so the benefit of a variable speed heat pump, as seen through the temperatures of the air, the source, and the higher temperature, the indoor temperature, as well as the refrigerant temperatures. For the same indoor and outdoor temperatures, we can slow the compressor down. It needs to pump less. It uses less energy. We've looked at air-to-air heat pumps. We've looked at air-to-water heat pumps. How about water-to-air? How about a typical ground source heat pumps? What are the temperatures? What's the source temperature? What are the refrigerant temperatures? What's the impact on efficiency? So we're seeing how temperatures affect heat pump power use and how temperatures change. The refrigerant temperature, almost always, it's about 30 degrees lower than the source temperature, and it's about 30 degrees higher than the higher temperature, which is often it's the indoor air, but sometimes it's hot water, sometimes it's other things. Let's take a look at a ground source heat pump. Ground source heat pump, we've got heat from the ground, and the ground, especially in the beginning of winter, might well be warm. The ground as a source might be as warm as 50 degrees. Much warmer than the outdoor temperature at that ground condition of 50 degrees might be 30 degrees. It might be December, but the ground is warmer. We use our rule of thumb, we subtract 30, and the refrigerant will be at about 20 degrees Fahrenheit. And now we're going to use this as a water-to-air heat pump, and we're heating indoor air at 70 degrees. And we use our rule of thumb, and the refrigerant will be 30 degrees warmer than that. It'll be at 100 degrees, and the compressor only needs to pump from 20 degrees up to 100 degrees. That is significantly less than before. If you remember before, with 30 degrees at the outdoor temperature, we had refrigerant at 0 degrees. We were pumping from 0 up to 100. Now we're pumping from 20 up to 100. That is why a ground source heat pump is so much more efficient. Now, as we move through the winter, the ground and the water that's returning from the ground to the heat pump goes down. As the winter progresses, as we move through January towards February and March, this can actually get colder, and it can go as low as 30 degrees, 40 degrees. Let's say it's 35 degrees. This is in November, and here we are in March. And so later in the winter, a ground source heat pump has lower water temperature. Our rule of thumb, we're going to subtract 30 degrees. The refrigerant's going to be down at, not 0, I'm so sorry, it's going to be down at 5 degrees Fahrenheit. Later in the winter, as we head towards spring, for the same outdoor air temperature, we might, in fact, we will be using more power with a ground source heat pump as the ground temperature and the return water temperature from the ground to the heat pump goes down. Now I want to introduce a new term. We've been using the term source temperature for the temperature of the outdoor air or the outdoor ground in winter. That's the source of the heat. Another word we use is the sink temperature, and that is the temperature that we are pumping the heat up to. And the sink temperature in winter for most heat pumps is 70 degrees. It's the indoor air. That's the case for an air-to-air heat pump. For an air-to-water heat pump, the sink temperature is higher. It can be anywhere from 180 degrees if it's very hot water, and it can be as low as 80 or 90 degrees for a radiant floor system. Sink temperature, that's the high temperature that we're going to go up to. It's not the refrigerant temperature, it's the temperature of where we're pumping the heat to. Source is the low temperature, sink is the high temperature. How about the two refrigerant temperatures? The low refrigerant temperature, we call that the saturated suction temperature. The high refrigerant temperature, we call that the saturated discharge temperature. We might also call that the condensing temperature, and the low temperature, the saturated suction, we might also call that the evaporator temperature. We're seeing all of these consistent relationships between the air temperature or water temperature, we call it the source and the sink temperatures, and the refrigerant temperature, lower than the source temperature and higher than the sink temperature. How does this relate to indoor setback, lowering the indoor air temperature? Let's take a look at some of those temperatures, both the air temperatures and the refrigerant, and see how it affects the efficiency. Okay, through this lens of temperatures, let's look at the effect of reducing the temperature in winter indoors, reducing the indoor temperature using a setback mode. So outdoors will be our typical 30 degrees Fahrenheit. Indoors, instead of running at 70, let's run it at 60 degrees. What's our refrigerant temperatures? We'll use our rule of thumb. We'll go with the 0 degrees Fahrenheit refrigerant temperature in the outdoor heat exchanger, and we'll add 30 to the 60. We've got 90 degrees Fahrenheit in the indoor heat exchanger. The compressor needs to pump from 0 to 90, and that is less than the pumping from 0 to 100 when the indoor temperature was 70. Thermodynamically, if we heat a building to 60 degrees, we will use less energy than when we heat it to 70. Now, this conflicts with guidance we've been receiving for a few years now that says that we should not touch the indoor set point, we should set it and forget it. It turns out that that guidance was based on research that was limited to very specific use cases. And we are going to see some active discussions from a thermodynamic point of view, ignoring things like backup electric resistance heat, ignoring some other factors. From a thermodynamic point of view, if you reduce your indoor air temperature, your compressor power will go down. Finally, as you start to think about heat pumps, you might think about how things change in different seasons. Let's take the use of ground source heat pumps to heat hot water year-round. The ground source heat pump in the winter is taking heat from beautifully warm ground, maybe 50 degrees as we start into the winter, and then 30, 40 degrees at the end of the winter, and it's heating hot water. What's happening in the summer? In the summertime, that same heat pump is taking heat out of the ground pretty efficiently. It might start out the summer at 40 degrees, and then through the summer it might warm up to 60 degrees. Let's compare that to an air source heat pump. An air source heat pump in the summertime is taking heat from warmer outside air. It's taking heat from outside air at 60 degrees, 70 degrees, 80 degrees, 90 degrees to heat the hot water. An air source heat pump in the summer is more efficient for heating domestic hot water than a ground source heat pump. So you want to be thinking about that. A ground source heat pump may not be the absolute most efficient way of heating domestic hot water because the source temperature is changing from winter to summer. And in the summertime, an air source heat pump has a better quality source of heat in the outside air. Interesting. Okay, let's recap. We have, with any heat pump, a temperature that we're trying to take heat from and a temperature that we're trying to put heat to. The lower temperature there is called the source temperature. The higher temperature is called the sink temperature. The refrigerant temperature, if we've got a source here and a sink here, for example, outside air at 30 degrees and indoor air at 70 degrees, the refrigerant temperatures are always lower than the source and higher than the sink. And a first estimate is, just for trying to understand it, maybe 30 degrees lower than the source and 30 degrees higher than the sink. As conditions change, as the indoor air gets cooler or warmer, let's say somebody turns the thermostat up, the air temperature goes up and the high refrigerant pressure and temperature goes up, the compressor needs to work harder. We're always keeping our eye on the temperature change from the low temperature to the very high temperature of the refrigerant. And that reflects how hard the compressor has to work, and that reflects on how much electricity we're going to use, how efficient the heat pump is. So, a second theme of this series of discussions is we're keeping our eye on those two refrigerant temperatures, and they follow the source and the sink temperature. If the outdoor air gets colder, the low refrigerant temperature goes down, the compressor works harder, we're paying more for electricity. If the indoor temperature goes up, the refrigerant temperature is going to go up on the high side, the compressor will work harder, we'll pay more for electricity. We are always trying to keep the source and the sink temperature as close as possible together. We like it when it's warm outside. We like to lower the indoor air temperature. That brings those pressures and temperatures closer together of the refrigerant. And that's what we're paying for the electricity. We can see all kinds of use cases and applications based on this principle right away. An air-to-water heat pump, taking heat from the outside air and putting it into hot water at 180 degrees, we know right away that will cost more. That will use more electricity than an air-to-air heat pump where we're just going from 30 degrees outside air temperature to 70 degree indoor air temperature. We know that if we reduce the set point of a domestic hot water heater that's heated with a heat pump, that will bring the water temperature down, will bring the pressure down and the temperature down of the refrigerant, and that reduces heat pump energy use. Anytime we can bring those two refrigerant temperatures and pressures closer together, we reduce energy use. And this is consistent. This is why we use variable speed heat pumps. It's why we try to set back indoor air temperatures in the winter time. And it's why we try and set indoor temperatures warmer in the summertime. Seeing heat pumps through the lens of temperatures explains so much. And a final thought. Now that you understand the relationships between the source temperature and the sink temperature, like 30 degrees outside air and 70 degrees indoor air, or 50 degree outside ground and 70-degree indoor, and that the refrigerant temperatures are just a little lower and a little higher, you can use that to start thinking about heat pumps for all kinds of applications. You could think of heat pumps for industrial applications. You pumping heat from an industrial process at one temperature, any temperature, up to another temperature. You can start to look at things through the lens of just the source temperature and the sink temperature, and then the efficiency. And you can compare heat pumps to heat recovery, for example, direct heat recovery. You can start using heat pumps for all kinds of applications. Once you understand that there's just the source temperature and the sink temperature, those are the things you're trying to heat. That's the sink temperature is what you're trying to heat. The source is where you're getting your heat from, and that the refrigerant temperatures are just going to be a little higher and lower. Now go out there and find ways to use heat pumps in all kinds of creative ways. Thank you.